Intro to graphs. What is a graph? A graph is a collection of vertices and edges that connect those vertices. Now, what does this sound like? This sounds like a couple of containers that we've already discussed before, namely the linked list and the binary search tree. And the reason for that is because the linked list and a binary search tree are specific kinds of graphs. They're graphs with specific shapes. A linked list has a linear shape, and the binary search tree has a tree like shape. And the reason they have that shape is because that optimizes them for the kind of problems they're meant to solve. A graph, however, does not have a specific shape. The shape of a graph depends on the situation it's representing. For example, a graph could represent a map, and each vertex in that graph could correspond to a location on that map. And the edges that connect those vertices could represent the time it takes to walk from one location to the other, right? Or the distance from one location to the other. In fact, it's not even required that the exact shape of the graph matches the exact shape of the map. All that matters is that the right vertices are connected to one another and that the numbers associated with those edges are correct. Now for some vocabulary words. Adjacent. Two vertices are adjacent to one another if they are connected by a single edge. For example, in this graph, vertex U is adjacent to V and vice versa. Also, vertex U is adjacent to W and vice versa. However, W is not adjacent to V and V is not adjacent to W. That's because there is no edge that connects those two vertices. Path. A path is a sequence of edges. For example, suppose this is my graph and I'm asked, what is the path from A to D? What I will then do is list the vertices in order that must be visited to travel from A to D, starting with vertex A, then C, then J, then D. Thus, the path from A to D would be A, C, J, D. It's also worth noting that this is not the only path from A to D. Right? We could have also gone from A to C, then from C to G, then from G to E, E to B, and then B to D. And that would have been a correct path as well, although it would not have been the shortest path. Undirected graph. An undirected graph is a graph where the edges have no direction, permitting us to travel in either direction on them. Meaning in a path, we can go from A to C and from C to A. We can go from J to D and from D to J. Both directions would be legal in an undirected graph. And a directed graph is a graph where you can only travel one direction along an edge, like a one-way street. So in this graph, for example, we can go from A to C, but we cannot go from C to A. We can go from I to J, but we cannot go from J to I. Connected graph. A connected graph is a graph where there exists at least one path from every vertex to every other vertex. Here's what I mean. Consider this graph, for example. No matter which two vertices I select in this graph, there will exist at least one path that connects them, right? For example, A and H. There's a way to go from A to H, and there's also a way to travel from H to A. Now suppose, however, I add one more vertex to this graph. I add vertex K. While this is still just one graph, this graph is no longer connected because there's no path to K, no matter what other vertex you choose. Vertices like K that have absolutely no edges coming out of it, we call those vertices an island. When working with directed graphs, however, the question of whether or not a graph is connected is a little more complex. In this case, we don't have an island, but that doesn't mean that the graph is connected. For example, there's a way to travel from I to J, but there's no way to travel from J to I, right? There's no way to travel from A to H. So in this example, this graph is not connected because there exists more than one pair of vertices we could select where there does not exist a path traveling from one to the other. Weighted graph. A weighted graph is a graph where each edge is associated with a weight. This weight, which is just a number, by the way, could represent a lot of things. A weight could represent the distance between two vertices. A weight could represent the time it takes to travel between two vertices. The weight could represent the cost of going from one vertex to the other, and many other things. This is just an example. And this is an example of what a weighted graph would look like. You'd have your vertices, you'd have your edges, and then you'd have a number associated with each edge. So for example, for the edge that connects A and C, the number 10 could represent the distance between A and C. It could represent the time it takes to travel between A and C in minutes, in hours, in nanoseconds. It could represent the cost of traveling from A to C, so on and so forth.